Translating sentences into equations, Level 1. Many applications in algebra require you to translate word sentences into equations. Recall that equations contain an equal sign between numerical and/or variable expressions. In the last video, we practiced translating words into symbols, converting the words into algebraic expressions. Now we're going to add an additional level of difficulty. Not only do we need to translate words into algebraic expressions, we also need to determine if the sentences describe an equation. Usually, the telltale sign that you are face to face with an equation is by scanning the sentence for phrases containing the word is, as in 5 more than a number is 10. After reading this sentence, we find the key word is. This means that we are face to face with an equation, so we must not forget to include an equal sign in our final expression. Let's try this example. The first part should be fairly easy. If it's not, I recommend you to check the previous video titled Translating Words into Symbols. Alright, let's go ahead and translate this sentence into an equation. The expression 5 more than a number translates to n plus 5 or 5 plus n because of the key word more, and remembering that when you add two numbers, the order is not important. Next, we add an equal sign because of the key word is. And finally, we include the number 10. The final expression is written as n plus 5 equals 10, or 5 plus n equals 10. Both expressions are acceptable ways of writing this equation. Alright, let's try some more examples. 50 decreased by a number is 20. We see the key word decrease, so we are dealing with a subtraction between two numbers, specifically 50 and a number. So this expression is written as follows: 50 minus n. We also see the key word is. So we write an equal sign followed by the number 20. Remember, when dealing with expressions with the subtraction operator, you need to be careful. Unlike addition, where the order between the two numbers does not matter, subtraction is order sensitive. And the expression n minus 50 equals 20 is totally different, as well as totally wrong for this particular example. So the correct answer is written as 50 minus n is equal to 20. Okay, let's try the next example. 7 less than a number is 12. Once again, we have the key word less, so we have a subtraction. Notice that the key word is less than. Remember, be careful with subtraction operators. At times, you can't just translate the expression in order. For this example, the expression 7 less than a number is written as n minus 7. Once again, we see the key word is, so we are dealing with an equation, so we insert an equal sign. And finally, we include the number 12. So the final equation is written as n minus 7 equals 12. Let's try the next example. The sum of 1/3 of a number and 10 is 30. Here we have a couple of key words. The first key word is sum, so we need to add two expressions. The first expression, 1/3 of a number, is denoted as 1/3 times n, because of the key word of, which translates to multiplication. Then we add the second expression, in this case, the number 10. And then we add the equal sign, because of the key word is. And finally, the number 30. So the final equation is expressed as 1/3 n plus 10 equals 30. Or written another way as 10 plus 1/3 n equals 30. Let's move along to the next example. 1/3 of the sum of a number and 10 is 30. This problem seems to look exactly like the previous example, but notice that it's actually different and requires the use of grouping symbols. We first have a product because of the key word of. So it's going to be 1/3 times the sum of a number and 10. So we use grouping symbols as follows. Then we include the equal sign because of the key word is. So we include the number 30 after the equal sign. The final expression is written as 1/3 times the quantity n plus 10 equals 30. Or written another way as 1/3 times the quantity 10 plus n equals 30. Keep in mind that some phrases require the use of grouping symbols. So make sure you read the sentence as many times as you need to completely understand the problem. Okay, notice that every single example up to this point contained an equal sign, immediately after some sentences. Let's try an example where the equal sign appears first, like the following example. 3 is 10 more than 5 times a number. In this example, we first write 3 equals, because of the key word is, which appears first, followed by a sum of 3 expressions, specifically 10 and 5n, because of the key word more and times. The final expression is written as 3 equals 10 plus 5n. Or alternatively, we can also write this expression by flipping the expressions on the left side of the equal sign with those of the right side of the equal sign, as follows. 10 plus 5n equals 3. Both of these equations are essentially the same. Some sentences actually describe equations that contain variables on both sides of the equal sign, like the following example. Twice a number is 10 more than a number. We first write 2n followed by the equal sign because of the key word twice and is, which denote multiplication and an equal sign, respectively, followed by the sum of 10 and a number n. Once again, we can write this equation by switching the expressions from either side of the equal sign as follows. Alright, let's try the final example. 9 less than 3 times a number is 10 more than the number. So here we have multiple things occurring on both sides of the equal sign. On the left-hand side, we have a multiplication and subtraction, specifically 3n minus 9, followed by the equal sign, and a sum of two numbers which include 10 and n. So the final expression is 3n minus 9 equals 10 plus n, or 3n minus 9 equals n plus 10. Either form is acceptable, because the order in which you add numbers is not important, but the order in which you subtract numbers is important. So keep this important detail in mind. Alright, in our next video we will continue translating sentences into equations, especially those that require the use of formulas. Translating sentences into equations, Level 2. In our previous video, we practiced translating sentences into equations. Now we will work on slightly more complicated problems that require the use of formulas to translate and set up the required equation. Let's first work on perimeter and area problems. Use the figure and the information given to write an equation in terms of the variable x. So here we have a triangle, and we are given the measurement of 3 of its sides. They are x, 5, and 8. And we are also given the perimeter, which is equal to 25. So we can express the perimeter of the triangle by adding all the sides. So we do just that and obtain the following expression, x plus 5 plus 8, which reduces to x plus 13. This expression represents the sum of all the sides of the triangle. In other words, its perimeter. And we also know that it is equal to 25. So the final equation is written as follows, x plus 13 equals 25. Let's try the next one. Here we are given a rectangle with the given sides. We are also given the perimeter and area of the rectangle. So we need to set up an equation that represents the perimeter and another equation that represents the area. Let's first set up the equation for the perimeter. We first need to add all the sides. Doing that, we have the following expression, x plus 8 plus x plus 8. This can be simplified to x plus 16. And we know that the perimeter is equal to 20. So the final equation that represents the perimeter is written as x plus 16 equals 20. Now, for the area of the rectangle, we know that it's going to be equal to the length times the width. So the length is equal to 8, and the width is equal to x. So we multiply these two expressions and obtain 8x. And we are also given that the area of the rectangle is equal to 16. So the final equation that represents the area of the rectangle is written as 8x equals 16. Alright, let's try the next one. Here, we are also given a rectangle with the following measurements. Notice that each side contains a variable. Nevertheless, the approach in writing the equation is the same. We are also given the perimeter and area of the rectangle. So let's first find the equation that represents the perimeter of the rectangle. So we add all the sides, making sure we use grouping symbols where needed. After taking care of that, we end up with the following expression. X plus the quantity x plus 1 plus x plus the quantity x plus 1. And now we set this expression equal to 10. Now for the area, we need to take the length and width of the rectangle and multiply them. Doing that, we have the following expression for the area of the rectangle. X times the quantity x plus 1 equals 6. Alright, now let's work on more problems that require the use of formulas. Let's try the following problem. Write an equation that represents the given information. The perimeter of a square is 100 meters. Alright, we need to translate this sentence into an equation. Notice that we don't have any information about the sides of this square. Usually when you don't know or have any information about a certain measurement or object, feel free to assign a variable to take its place. In this case, we will use L for the length. Remember, you are free to choose any variable you want. Now we need to relate this variable with the information given. We know that in order to find the perimeter, we need to add all the sides. So the perimeter can be written as L plus L plus L plus L. And we are given that the perimeter is equal to 100. So the final expression is L plus L plus L plus L equals 100. Or we can multiply a side by 4 instead of adding them, since the square sides have the same length. So an alternative equation is 4L equals 100. Alright, let's try the next one. A dozen donuts cost $5. Once again, after reading the sentence, notice that we have no idea how much a single donut costs. So this value is a perfect candidate to be represented by a variable. Let's use D as our variable. Okay, so now in order to find the total cost, we use the cost formula, which is equal to the number of items times the price of each item. In this case, we have a dozen donuts, which is equivalent to 12. And we multiply this value by the price of each donut, which is represented by the variable D. Then we know from the sentence that this has to equal $5. So the final equation is written as 12D equals 5. Let's try the next one. 7 years from now, a trading card will be 40 years old. Alright, first thing we need to do is to identify the variable for this problem. Reading the problem, we notice that we have no idea what the present age of the card is. So we use the variable C to represent the card's present age. The phrase 7 years from now implies addition, so we need to add 7 to the card's current age, which is represented by the variable C. We also know that after 7 years, the card will be 40 years old. So the final equation is written as C plus 7 equals 40, or 7 plus C equals 40. Let's try this one. A student solved all but the last 2 problems in a homework assignment of 10 exercises. Like always, we need to identify the variable in this problem. From the looks of it, we have no information about the number of problems that the student has solved. We will assign this quantity as the variable, and use the letter P to represent this unknown quantity. The student has done all but 2 problems, meaning that the total amount of problems is equal to the sum of the problems the student has finished plus the problems left unsolved. This is written as P plus 2, and we know that there are a total of 10 exercises. So the final equation is written as P plus 2 equals 10, or 2 plus P equals 10. Alright, let's check the following sentence. A train traveled 463 kilometers at a rate of 132 kilometers per hour. This looks like a classical distance equals rate times time problem. We are given the distance, which is equal to 463 kilometers, and we are given a rate, which is 132 kilometers per hour. What is not given is the time, or in this case, the hours traveled. So we will let that value be represented by the variable t. So the final equation is written as 463 equals 132 times t, or 463 equals 132t. Alright, let's try the final problem. The sum of 3 numbers is 100. The second of the numbers is 5 less than the first, and the third is 9 more than the first. Alright, when dealing with these types of problems, it's okay to read it over and over again until you completely understand it. We are definitely provided with various pieces of information. Let's break it apart and look at each sentence systematically. We know that we are going to add 3 numbers, and that their sum is going to equal 100. So we need to determine what those 3 numbers are. From the sentences, we have information for the second number and third number, but we have no information about the first number. This means that the first number is a perfect candidate to be represented by a variable. So the first number will be denoted by the variable n. Now that we have determined what the variable represents, in this case, the first number, we can use it to write the second and third number in terms of this variable n. The second number is 5 less than the first. This translates to n minus 5, making sure we use grouping symbols when adding the quantity n minus 5. And the third is 9 more than the first, meaning it's n plus 9 or 9 plus n. Again, making sure we use grouping symbols when adding the quantity n plus 9. So the final equation is written as n plus the quantity n minus 5 plus the quantity n plus 9 equals 100. This final problem contained a relatively large amount of information, but was manageable by systematically translating each phrase one by one and determining what the variable should represent. In this problem, it turned out to be the first of the 3 numbers. Alright, in our next video we will use all the skills that have been developed up to this point and further increase the difficulty by translating actual word problems into equations.